task. So pulling up lecture 3 then to start with. All right, new topic. So first off, reminding us where we've been. Because the semester's halfway over, we've been through a lot. So generalized linear models, big picture, is that you're taking what we used to think of as a model and we're adding 2 new twists to it. So what we used to think of as a model is now called just the linear predictor. What predictors go in? Do they have main effects? Do they have interaction terms? Do they need nonlinear slopes? All that stuff, that's linear predictor. The new 2 things that we have to figure out is what kind of link function do we need? And when do we need link functions in a general sense? When do we need them?
When your outcome is not continuous.
Yes.
And has weirdness.
It has weirdness. Yes, when your outcome has boundaries, I would say, is the general thing. So not continuous, meaning you have to worry about predictions that go out of bounds. That's when you need to think about a link function. And then the other part of it is if the residuals aren't normally distributed, and really normally distributed is not the issue, it's constant variance that's the issue. If your residuals do not have constant variance, then what is a better match for what distribution they take? And basically the match comes down to what kind of outcome it is. So we're talking about counts in this unit, and counts are bounded at 0, so we'll need a link function, but it will be a different link function because counts can go on forever. And the big trick with counts is what kind of variance-related distribution thing do we need? So so far with respect to links, we've seen logit, we've seen probit. Are those basically the same thing or are they different? Basically the same thing by a factor of 1.7. Probits are z-values on a standard normal distribution. Logits are log odds. They both take a bounded outcome of probability and transform it into something that is unbounded and continuous in both directions. Log and c-log, what are those for? They can be for anything. You can use these link functions with any type of outcome because even if the outcome is categorical, each submodel is binary. So when would you consider a log or a c-log?
I know it's frequency of what I also can't remember which one.
I don't remember which is which either, no.
Log, I think it is for when you have more ones, and complementary log when zeros are more frequent.
Yeah, so when you have a severe asymmetry in the zeros and ones. I want to say complementary is for more zeros.
I think, yeah.
I thought I had a mnemonic for that, but now it's gone. So just as an example, Kelly, so several of you know her, she's in sociology, she's working on a master's thesis right now, where she's predicting an outcome where 97% is 0 and 3% is 1. So she's looking into the complementary log family for that reason. If you're not sure, AIC or BIC can help you weigh in. Smaller is better with respect to which one fits better, or would work better. I want to say fits. That's not quite the right word. But the variance part with respect to the residuals and what conditional distribution they follow, it's Bernoulli for binary or multinomial for ordinal nominal, the end. Now where we're at is counts, where we have to worry about all this different stuff. You a question?
Yeah, is a Bernoulli distribution just a collection of binary trials?
Bernoulli is a special case of binomial for one trial.
Okay.
And it's a dude's name, which is why it's always capitalized. I think. I'm pretty sure. Whereas multinomial is not someone's name. Although it could be. That's when you know you have a child of 2 statisticians, right? When they name their kid multinomial. Or multi for short, you know. Jonathan wanted to name Huey Mahalanobis. I had to say no to that one. It's a really good thing that he wasn't a girl, by the way, because there was no way we were going to agree on a name for that. But we both decided that Hugh Hoffland sounded like a badass name, and so we went with that. Yes, for those of you who don't know, my son has both our names put together. So I'm Hoffman and my husband is Templin and his last name is Hofflin. We made a new last name for him because Hoffman Templin sounded like a law firm to me. So he has a whole new last name. And yes, you can do that, at least in the state that we lived in, Kansas, where he was born. But anyway, so counts is going to be, the easy part is the link. It's going to be log. There are other choices, but I've never actually seen them used, and they're hella confusing. So log is going to be our story. The issue is going to be what happens with respect to the residuals and whether or not we need some kind of extra variance relative to what the distribution expects. So then next, it will be probably after spring break, we'll get to other kinds of bounded outcomes like proportion correct. That will be a logit plus some kind of binomial or beta binomial hybrid and skewed continuous for that one. And then we'll also talk about hurdle variance for continuous outcomes later. So we have, after this unit, one more unit before we switch to talking about multivariate. And that we will have covered most of the things that I've ever seen or heard of with respect to generalized models. I'm sure there's more, but we've hit the high points. So a taxonomy then of what we've covered so far, you'll see it written this way. And I say this because some choices work for outcomes they're not designed to, but the reverse is not necessarily true. So what we've actually been talking about so far is what people would call discrete outcomes. So categorical variables in which they're not really numbers, even if we use numbers to represent the different categories. And the question that we have to answer then is, are they ordered? And that dictates what kind of link function we want to use. Count variables is where we're at now, where counts are discrete integers. Like you can't smoke half a cigarette. I'm sure you could try, but it counts as one. Or have half a car wreck. Something like that doesn't work. So this is still in the world of discrete. So the distributions that we're working with for counts do not have decimal values in them. Essentially, they're for whole numbers. Continuous outcomes then is things like response time or cortisol levels or things like that where it really could be any number, even non-integer numbers. So models that work for continuous outcomes could be used on counts, but the reverse is, hang on. Yeah, the reverse is not true. If you have something that's continuous, you can't use a discrete distribution for it. You can take a discrete outcome and pretend it's continuous, though. So the choices are relative to whether or not you have possible values in between once we get into numbers or numbers, which is where we're headed here. So the same issue with respect to boundaries that we saw for proportion or probabilities or proportion correct type things is true for counts. Counts can't go negative. So if we had a regular old linear predictor predicting a count, we do not want the boundaries to go below 0. And the way that we solve that is to predict the log of the count instead. So once we back translate what the model predicts onto the original count metric, it shuts off at 0 like it's supposed to. So you can't, so then the model does not predict counts that go below 0. So the slopes are linear with respect to predicting the log count. The slopes are nonlinear with respect to predicting the original count. And they're nonlinear with this sort of exponential function. So the red one would show a negative slope. The blue one shows a positive slope.
I have a quick question about counts.
Yeah.
When you back translate it, like what the model says, I'm assuming that might have decimals.
Yes.
Okay.
Yes. Because we are predicting the log of the expected count. And the expected count can have decimals. Yep. Yeah, that's actually what's coming next.
Oh, great.
Thank you for that transition. That was very helpful. So we're using a log link to predict the log of the counts as the y-hat that's given by the linear predictor. And the inverse link then is just e to the count. So the exponentiation that we saw in the previous unit is back again. So for instance, if the model predicts the log of the count as -1, if you unlog that, if you exponentiate it, it comes up with a predicted count of 0.368. So like you can have a predicted count that is not a whole number. You can have the average of a count that's not a whole number, but the original count is a whole number. So it's the exact same concept as what we had previously were just zeros and ones, but we're predicting probability, which is continuous between 0 and 1. In this case, what we really have is 0, 1, 2, 3, 4, 5 counts, but we can predict things that are in between. And your question last time, Vladimir, about offsets. An offset is a way that you can control for differences in the amount of time in which the count was observed. So if you have an outcome variable that's like count of events per day, and somebody else has something that's count per week, you need to correct for differences in the possible amount of time that the counts could happen in. That can be done via what's known as an offset. A synonym for that I've seen is exposure. And that amounts to adding in a predictor variable for the time that has passed whose slope is fixed to 1. So it's not being estimated as a slope, it's just in there to help control for the fact that you have different amounts of possible time. And all of the count software that I've seen has a way to put that in there. That's a pretty standard thing. And effect size is the same thing that we've been doing with yet a third name. So if you take a slope that predicts the log of the count and you exponentiate it, it is now called an incident rate ratio. So it's an odds ratio or a relative risk ratio or an incident rate ratio. They all get computed the same way. So for instance, if I had an incident rate ratio of 1.25, then I would say that the counts are 25% bigger if you have a 1 for the predictor rather than a 0. And if it's an incident rate ratio of 0.75, then that describes a negative slope, and I would say that the counts are 25% lower. So these have the same problem that causes me to hate odds ratios, in that a positive slope effect size is somewhere between 1 and infinity. A negative slope effect size is shoved between 0 and 1 in this weird asymmetry that I just don't like. So this is the easy part. We're going to use a log link. The model's going to predict the log of the count. We can unlog it, and yes, I will keep using that term even though what I really mean is exponentiate. We will unlog it, and you can get back to the original count, and you can get something that resembles an effect size if you unlog your slopes. The hard part is going to be which conditional distribution do we need? Question?
So when you say adjusting for offset, adjusting for time, do you mean like, so let's say, because I looked up Poisson distribution on Wikipedia or Google, and they said like,
This is it.
Yes, but
Yeah.
like a real life example, like number of calls an ER would get during certain hours of the night. So it'd be like, would offset be if the time they measured was different for each?
Yeah.
Oh, okay.
Yeah, it's because a count is essentially like a rate out of some amount of time. And if different subjects have different potential amounts of times, then their counts are going to be different for that reason alone.
Okay.
And offset adjusts for that and turns it into something that's more like a rate.
So it'd be like, we got 3 calls in the first half hour, and like between 6 and 6:30, and then we got 5 calls between 7 and 8, and then comparing, like adjusting since the first period was half hour and the second period was an hour.
If those were separate cases in the data, then yes.
Okay.
Yes, just like for separate subjects. If people are observed for different amounts of time, their counts will differ for that reason.
Okay.
You need to adjust for it. That it's preferable to do it this way rather than to convert it to a rate, from what I understand. So offsets are used for that. So I will tell you that this idea of what kind of conditional distribution goes with your count is easily a semester-long course in and of itself. There are so many choices. So we're just going to hit like the highlights. The highlights that I have 5 different models, okay, and to me that's just the highlights. But that's out of several others that exist and that people fight over which one is the better one. So this is the standard one. But when people talk about count regression, sometimes they call it Poisson regression. And what they're referring to is actually the distribution that goes with the model. So everything's going to be log length. The question is what kind of distribution. And Poisson is a distribution in which the mean and the variance are the same. So it's another one parameter distribution. So as your predicted count increases, the variance around it is expected to be equal to that predicted count. So it creates like a fan shape where like the residuals are expected to spread out as the count goes up, but only to some extent. So these are examples, I stole this from Wikipedia as per my usual, of count distributions with different means. For whatever reason, they decided lambda would be the name of this parameter, not to be confused with the factor loading, which is what lambda usually is when I see it. So lambda equals 1 means an expected, a mean of the count distribution of 1 is also its variance, would create a distribution that looks like this orange one. And the reason that these are dots is because it's a discrete distribution. So it's recognizing that you really can't have anything between 1 and 2 as a possibility here. And a mean of 4 for a count distribution would look like this purple one. And then by the time you get out to a mean of 10, it looks normal-ish. So there are various guidelines as to when you have enough counts to say, screw it, normal's fine. And I've seen like 6 or 7 as sort of the minimum of that. I would probably still work with the count family unless I absolutely was forced into something else for other reasons. But as you can see, it starts to look normal, for lack of a better word. But normal as a distribution has constant variance, whereas Poisson has non-constant tied to the mean. So they're still not the same, even though the shape looks the same. And this type of model is available in Glimix. Stata has a package that's called Poisson, but we're going to use one that's called GLM instead because it has more options in terms of fit information. And in R, there is the GLM function has a Poisson family, and then there's also VGAM. I found a couple more too there's a lot of choices for that. All right, so this is the first distribution. This is hardly ever going to work, though. It's really restrictive to say that the mean and the variance are exactly the same thing. So there's 3 potential ways that this could go sideways, and the Poisson would not be a good choice. Problem number 1 is when the mean and the variance are not the same. It is technically possible that you could have variance that is less than the model thinks, which is called under dispersion. I've never seen that happen. What is far more likely, and what I have seen happen, and the example that I have for you shows this, is over dispersion, where there's more variance than what the model predicts under a Poisson distribution. So we got to add something to the model that allows the variance to exceed the mean. And the big question is, how do we do that? Do we just like add extra variance, or extra variance that increases as the mean increases, or some other kind of nonlinear function? So that's where all of the different varieties start to pop up as to exactly how the variance exceeds the mean. But too much variance is the big picture idea. Another problem, which is not really a problem, but it means you need to switch to a different distribution, is if there are no zero values. So for instance, if I'm looking at number of days in a hospital stay or something, and I get my data from a hospital, the only way that somebody gets in that data set is if they went to the hospital and they were there for 1 day. So no one in my data set is going to have a 0-day hospital stay by definition. And when I first was reading about this was not 2 years ago, this is before that, I was like, well, I'll fix that. Subtract 1, done, right? It doesn't work. So if you have a distribution that's a count that starts at 1, you can't just subtract 1 to say, I got my zeros in here after all. It doesn't work. So just putting that out there. There are what is known as zero-altered count distributions that take into account that you can't have zeros and adjust everything accordingly. Those are harder to find, but they exist. And then number 3, when there are too many zeros. And this is also very common, and there are 2 main ways to fix it. One makes no sense to me, and the other makes a lot more sense, but is harder to do in software. So we'll see more details about each of these, but this is the sort of the big picture as to why Poisson is not going to be the end of the story in most cases. All right. It's 1:36. I want to do some foreshadowing. Can I do that?
Yeah.
Okay. I'm going to example 3. So this is the example that I'm going to give us in next week. Since it's not garbage day, that means it's happening next week. Predicting count outcomes, and this is a true story. Okay? So the end result of the story is this paper right here that I helped a graduate student, Rosie, the lead author, publish in 2015. This was her master's thesis. And this whole thing, the study was done, the data were analyzed, and she had a manipulation that she was saying was going to result in a significant interaction term. And these were, hang on, let me get to it. This was her result. A p-value for the interaction term it was like 0.06 when she came to my office. And her question was, what kind of transformation should I do to make my outcome more normal? And I said, well, tell me about your outcome, and do you have a histogram I can look at? And she said, sure. And here is the histogram. It's a count outcome. It is number of mean things said during an experimental session where they were deliberately trying to get people to fight with each other. Yeah, I know. And so most people were not mean.
How did that get past IRB?
Because it was for science. Like, you can read about
those sleep studies that are approved. Stop messing with people's sleep.
But you can read about more details in the paper. I'm over sort of simplifying for the purposes of my discussion. But this was her question, was what kind of data transformation can I do to make this more normal? And I think the root of the question was because my p-value is just barely not significant, and can I like fix it somehow? And my first answer was there is no transformation. That's going to take this 45% of the sample that answered 0 and spread it out. This is a constant. Like that's mathematically not possible. But a better question is, like, why are you fitting an ANOVA, which is what this model was, to a variable that looks like this? Well, to be fair, this is the marginal distribution, and so it could be that the residuals look more normal, but here's the residuals when you break it down by condition. No, this is not normal. So I tried to explain to her, well, you can do an ANOVA, but you need to be using a count model for your ANOVA. And this was at the time when Jonathan and I were team teaching a course where this was going to be like the next unit. And I'm like, oh, can I use your data for this? And I built a whole course example. And spoiler alert, once you fit the right count model, you get a very significant interaction. So it worked out a beautiful story. And I remember her being very concerned, like, how would I explain this to people? Like, they're going to be like, why didn't you do an ANOVA? It's like, you need to tell them you did an ANOVA with a negative binomial distribution. And then it worked out being okay. So that's the story that I have to tell you about. It's real data. And in this example that we're going to do next week, it's the same model every single time. All the thing that changes is the conditional distribution, but the results differ wildly with respect to the significance of her simple slopes and the interaction terms. So that's coming next week. Does that sound like an exciting story?
Yeah.
I think so.
What does the negative binomial distribution look like?
Great question. This thing.
So is it like,
Negative binomial is if you took the Poisson and just like stretched it out over to the right-hand side. So there is a parameter that's added to it that is a multiplier of the variance. So it is called K in the most common notation that I'm working with, and it's k times the mean squared, so it allows the variance to exceed the mean in a quadratic fashion. And this is what it looks like. I didn't steal this. I made this picture all by myself, for once. And so the difference then, the blue line is a Poisson distribution if you had a mean of 5, and so the variance is 5. The red line is still a mean of 5, but following a negative binomial distribution with a stretchy factor of 0.25 that allows the variance to be 11.25. So you can see that it has like a bit of skewness here. The same is true with green versus purple. Green is a Poisson with a mean of 10 and a variance of 10. Purple is negative binomial with a mean of 10 and a stretchy of 0.25 that brings the tail out. So negative binomial is a hack that someone figured out works for skewed count data. The actual negative binomial, like where it started from, was the number of trials that had to pass before something happened. Remember correctly? And somebody figured out how to reconfigure it so that it worked for this problem instead. So then the question is, which kind of negative binomial? And there are 3 on this slide alone, and there's others that have been developed as well for exactly how the stretchy should allow the variance to exceed the mean. So I'm going to show you the most common one.
Calculating k, like
Yep.
how it estimates k.
Not how it estimates, how it specifies it.
Specifies, okay.
Yeah, so there's negative binomial 1, which just added variance, and that one turns out to not work very well. And then there's generalized Poisson that does it differently. So there is a difference with respect to how k is parameterized, which solves a problem of it being undefined when k is 0. But the negative binomial 2 is the one that I've seen most commonly and the one that's built into most software. So that's the one that I'll show you. But there's a whole bunch of these. So we're going to use Glimix. In Stata, there is an nbreg command and a glm command that will do this, and it will actually use both because one gives you something that the other does not, and vice versa. And in R, there's a couple different packages. The mass package, which I think, Nathan, you had sent me for categorical data, has a negative binomial addition for Poisson, and then PSCL is another one that I found that does zero inflated models. So whole bunch of different possibilities, but that's what we get to do. Stretchy Poisson. That's coming next week because it's 1:43. And everybody looks overwhelmed.
It's just midterms. We have our IRT class has our midterm on Monday, so.
Well, don't worry. Stressing about midterms will not help you do well on them.
We also went over that, like confounding multidimensional stuff with data for anxious.
Okay. So I shouldn't take it personally that people are looking overwhelmed, is what you're trying to tell me.
Yeah,
That's fair.
I'm
All right.
nervous for it, but I might get nervous for
Okay.
good exams.
Any questions before we wrap up then? Let you go study? Okay, then thanks for being here. Have a good weekend. Do your formative assessment by Monday night if you can, please. Good luck on your midterms.